So hi everyone, I am Thibault Delhaye and I come from the Catholique University of Louvain in Belgium. And today I will talk to you about our high efficiency wireless power transfer for millimetric size biomedical implants. I will firstly start with a small introduction and by talking about the state of the art. So nowadays, full of applications are emerging for biomedical implants. For example, we can try to measure neural signals with a chip directly implanted into the brain and try to create a new path, for example, for the neural information for the patient suffering of Parkinson, for example. We can also try to measure blood pressure for patients suffering of heart insufficiency. Or another example is the monitoring of glucose level for the patient suffering of diabetes. All these devices need power to make their jobs done, going from tens of microwatts to tens of milliwatts, and it seems quite difficult to open the people's body to replace the battery every time. So a classical way to power these devices is the inductive ferrite transmission. And the classical implementation is this one. There is two coils. The primary coil that stays outside of the body and that is connected to the power supply, and then secondary coil that is implanted directly into the body of the people. We place the primary coil in proximity of the secondary coil and we turn the power on. And the current flowing alternatively in the primary coil will create an alternative magnetic field that is partially intercepted by the secondary coil and that will create by Faraday's law a difference of voltage that can provide power to the load. The portion of the magnetic field that is intercepted by the secondary coil is called the coupling factor, K. The requirements for this type of devices are the size of the implant that can be maximum 1 or 2 centimeters, the working distance depending on how deep the implants will be implanted into the body. It can be up to 5 centimeters. The power that needs to be received, that can be so from tens of microwatts to tens of milliwatts. And finally, the low specific absorption rate for respecting health standard that needs high efficiency to limit the emitted power needed. To meet these requirements, few ways of improvements are existing. For example, we can add to our system an impedance matching system to reduce the reactive power of the system and so improving its efficiency. We can also add a ferrite core in the coil to improve the coupling factor between the two coils. And finally, we can add a control unit system as a phase lock loop to track the frequency that allows the highest power transmission. In terms of comparison with the state of the art, we choose to compare the efficiency of the different devices regarding to a scale factor, which is the distance between the coil, little d, divided by the diameter of the secondary coil, the big D. And I can now show that our system seems to be very interesting in terms of efficiency regarding to the scale factor. And particularly, I can show that efficiencies of 1 to 2 orders of magnitude higher than the state of the art have been obtained. But what is included in our high efficiency wireless power transfer? We choose to build our system around a 7.5 millimeter long, 1 millimeter diameter ferrite core of relative permeability of 35. Around that, we handmade 31 turns of copper wire of 100 microns diameter, and we fixed all this together using UV curing adhesive. And this led to a tiny coil of 3.65 microhenry inductance, and the resistance varies from 200 milliohms DC to 8.45 ohms at 14 megahertz. As power transmission circuit, we choose to keep it simple and only using an impedance matching system, which means that the resonance frequency of the emitting and the receiving circuits are the same. And with this simple system, the only thing that is a little tricky to know is the coupling factor between the two coils that we will have to measure. After that, all you have to optimize are the capacitor's value of the system. you also have to choose the primary coil and the working frequency. All of this led to a 5 degrees of freedom system that we have to determine to have the highest power transfer efficiency and a low input voltage for a given power needed by the load. To choose all these variables, we used a genetic optimization algorithm that uses a model F to evaluate the efficiency and the input voltage needed by the system for a set of variables. The first step is the initialization. A population of 200 samples is randomly generated and evaluated. After this, we choose the 100 most interesting samples and we operate operations on them, like crossovers between them and mutations, and we repeat this task 100 times. At the end, we kept the best solution of the optimization. Graphically, we can firstly see the constellation of the performances of the population 0, and we see that from iteration to iteration, the solutions are converging to a Pareto front, which is a set of the best solution. And for our system, we choose to keep the solution with the highest efficiency. After optimization, we build our system and we made a set of measurements. Firstly, we observe the evolution of the coupling factor, and we see that it decreases with the distance between the coil, which is the instinctive behavior that we were waiting for. And also, we see that the presence of ferrite core increases the coupling factor by a factor of 10. So the utility of the ferrite core is absolutely relevant. A second set of measurements has been done to measure the power transfer efficiency. And we can see that for our system, efficiency around 21% are obtained at 1 centimeters with a working frequency of 1 megahertz. This leads to negligible attenuations in tissues. In conclusion, we demonstrate a design system of an high-efficiency millimetric size wireless power transfer made of an handmade tiny coil with an inductance of 3.65 microhenry and an optimized resonant impedance matching system. This system demonstrates maximum efficiency of 21% at 1 centimeter, which is the best of the literature for the size of the implant. This system can deliver 1 milliwatt to a 560 ohm load at 1 megahertz. And finally, it shows negligible attenuations in tissues. Thank you.